Hello everyone. Today we will be starting a new chapter in our short course series. It's called Systems of Equations. And in the first part of this series, we will be discussing linear systems of equations. However, the schedule for this series is not yet determined clearly, so depending on some conditions and external factors, we may or may not be able to continue this series. But let's hope the best and assume that we will be continuing with this series. Anyway, let's take a look at what we have for today's course. We will mostly be focusing on how to solve equations, and for this course, how to solve linear equations. We will be visiting two different methods for solving equations. The first one is plotting the graphs of given functions, given equations, and finding the roots or the required values or points using these graphs. The other method we will be seeing is the substitution method. It's used widely in engineering problems, so it's very important that you should be familiar with substitution methods. And lastly, we will be discussing the elimination method and how do we solve the equations by using elimination. Of course, these are for linear systems, and for quadratic systems or for equations with higher degrees, these methods can still be used, but in a different way, and there will be different methods for higher degree equations. By the way, the functions within these equations in the scope of electronics engineering are not limited to polynomial functions. So there are power functions, logarithmic functions, etc. There are too many functions. So hopefully we will be visiting all of them, or at least some of them. Let's start with solving systems of linear equations by graphing. A system of linear equations consists of two or more linear equations. This section focuses on only two equations at a time, and the solution of a system of linear equations in two variables is any ordered pair that solves both of the linear equations. So when we are talking about a system of linear equations, this means that we have multiple linear equations. So it's not just solving one equation, but solving two somehow interrelated equations at the same time. Let's start with an example. It's about a solution of a system. The example says, determine whether the given point is a solution of the following system. The point is -3 and 1. So in the x coordinate it has -3, and in the y coordinate it has +1. The system consists of two functions, two equations. The first one is x minus y equals to -4, and the second one is 2 times x plus 10 times y equals to 4. So we have the point, so the question is an easy one. We'll plug the values into the equations. For the x coordinate, for the x value, we have -3, and for y, we have 1. So the first equation becomes -3 minus 1, which is -4. And the second equation is 2 times -3 for x plus 10 times 1 for y equals to -6 plus 10 equals to 4. So since the point -3 and 1 produces a true statement in both equations, it is a valid solution. For many of you, this might be a quite easy problem, but we are also aware of that some of the students are still struggling with solving equations, and solving equations is very crucial in advanced topics in electronics engineering and electrical engineering. So we want to be sure that everyone is capable of solving these equations, or remembers how to solve at least essential equations. Another version of the previous example is determine whether the given point is a solution of the following system. The point is this time 4 and 2, 4 for x and 2 for y. Then the system consists of again two equations. First one is 2 times x minus 5 times y equals to minus 2, and 2 times x plus 4y equals to 4, and this is the second one. Again, we will plug the values into the equations. The first equation becomes 2 times 4 minus 5 times 2 equals to minus 2. And the second one becomes 3 times 4 plus 4 times 2 equals to 12 plus 8, which is 20. And as you see, which is not 4. So since the point 4 and 2 produces a true statement in only one of the equations, it is not a valid solution for this system. So it satisfies one of the equations, but it does not satisfy the second one. So even though this point is valid for one equation, it is not a solution for the whole system. These basic examples are put here to put an emphasis on this difference. Since our chances of guessing the right coordinates to try for a solution are not that high, especially for complicated functions and equations, we will be more successful if we try a different technique. Since the solution of a system of equations is a solution common to both of these equations, it would also be a point common to the graphs of both equations. Good point. So to find the solution of a system of two linear equations, graph the equations and see where the lines intersect. This last bullet is the key of this method. Here in this example, we have a chart on the right part of the page. And here you see three oddly large ellipses of black color. These are just the points, but a little bit distorted because of some unknown error. So just think these ellipses as black points representing the given point coordinates, like 0, -6. And we have two lines here in this graph. As you can see, they are intersecting at a point, but they have totally different angles and slope. The question asks us to solve the following system of equations by graphing. So we already have the graph on the right side. The system consists of these equations. The first one is 2x minus y equals to 6, and the second one, x plus 3y equals to 10. And first thing we should do is to graph 2x minus y equals to 6, and it's already drawn in the right side. As you see, which line belongs to which function is not written here, so we have to find it ourselves. The easy trick to find the line, or let's say the graph of a function, is to try the points they intersect the axis. For example, let's take a look at this line. This intersects with the x-axis on the point 3, 0. This means that the x value is 3 at this point and the y value is 0, as you see. We can try this point within the function and we can see if this graph, if this line belongs to that function or to the other. So what we will do is accepting x as 3 and y is 0, and we will look if it satisfies. 2 times 3 minus 0 is equal to 6. Yes, it is. That's correct. So this line must belong to the first graph. The second graph, this one, should belong to x plus 3y equals to 10. These lines appear to intersect at the point 4, 2. So this means that this point exists in both equations, in both functions. And the result, if you give the x value of this point, the result of y would be same for both functions. Although the solution to the system of equations appears to be 4, 2, that point, we still need to check the answer by substituting x equals to 4 and y equals to 2 into the two equations to see if it really holds. In the first equation, we get 2 times 4 minus 2 equals to 8 minus 2 equals to 6. And in the second equation, we get 4 plus 3 times 2 equals to 4 plus 6 equals to 10. So the point 4, 2 checks, so it is the solution of the system. We have another similar example here. The given system consists of two equations, and we also have the chart on the right side. But I guess you may ask, how do we draw these graphs if these graphs are not given within the question? Since the technique requires us to graph these charts, a question most likely will not give these charts already, so we have to draw these graphs using the given equations, and this is the essence of this technique. And in this example, let's also check how should we draw these lines representing these functions. If we already know that the given equation belongs to a linear system, which means that the equation is a linear equation, then intuitively we understand that the plotted graph of the function should be a line, because if the function is linear, then its graph should be a line. And to draw a line, we do need at least 2 points, and if we have 2 points, then we can draw the line of the function properly. And in order to draw that, the first thing we should do is to check the points that this line of the function intersects with the axis. Any given line may not intersect with both of the axes, the x and y axis, but it should be intersecting at least one of them. Otherwise, it cannot be a line. It can be a line segment if there is a boundary on these variables of x and y, but if there is no boundary, or the set of the possible solutions of x and y is included in an unbounded number set, like whole numbers, real numbers, etc. If there is no strict boundaries, then this must be an infinite line and must intersect with at least one of the axes. And in order to find the intersection points with axes, we should set the variables 0, 1 by 1. If we set x to 0, we will get minus 0 plus 3y equals to 6. And this makes y equals to 6 over 3, which is 2. So this means that whenever x is 0, y becomes 2. And this is that point. On the other hand, we will now set y equals to 0 and evaluate for x. If y is 0, 3y becomes also 0, and minus x would be 6, and x would be minus 6, and this is that point. So when we get these 2 points, it is easy to draw the line as the graph of the function. Then we will not need any other thing. The slope is defined, the angle is defined, we know everything. For the second graph, we do the same. First, we set x to 0 and get the value for y. And then we set y to 0 and get the value for x. And we can then draw the line for the second function. And the lines here appear to be parallel. And how do we be sure about this parallelism? So these lines could be drawn to look like parallel, but they may not be indeed parallel lines. So we have to check if they are really parallel or just look like parallel lines. What we should do is to compare the common points. For example, we will first evaluate for this line 0, minus 1. This means that when x is 0, this function becomes minus 1 on the y-axis. And for the upper line, when x is 0, we get y equals to 2. And we can now look for another point which has the same x value or same y value. Let's look at this point. It has x equals to 6 and y equals to 1 for this line. And for the upper line, when x is 6, y becomes 4. So in these points, the difference on y values was 3. And here, when we are looking at these 2 points, the difference on y values are again 3. So this means that these 2 lines can never intersect at any given point. And this is the proof of the parallelism. Although the lines appear to be parallel, it is still required to check that they have the same slope. And we can do this by solving for y. And this is an alternative approach to check the parallelism using an analytical process. It is also possible to check this parallelism using the graph itself, as we have already done. For the first equation, minus x plus 3y equals to 6, and 3y equals to x plus 6 if we add x to both sides. And then if we leave y alone here, y equals to 1 over 3 times x plus 2. And for the second equation, 3x minus 9y equals to 9, and minus 9y equals to 3 minus 3x plus 9. And if we get y here, it is equal to 1 over 3 times x minus 1. So both lines have a slope of 1 over 3. So the angle between both of these lines and the x-axis are the same. and their slope is the same. So they are parallel and do not intersect. And as they do not intersect at any point, there is no solution for this particular system. In this example, we will be visiting another special case. Say, solve the following system of equations by graphing. Equations are x equals to 3y minus 1 and 2x minus 6y equals to minus 2. What we should do here is the same for the first step. We should plot these equations on a graph. And what we will get here exactly will be the graph you see on this page. And you see here only one line, although we have two functions. And the reason why is actually if you try to draw the functions, you will have to draw two functions, but these lines passes through exactly the same point. So these lines appear to be identical. We actually here have two lines, but they are standing on top of each other and they look like there is only one single line. Although the lines appear to be identical, we still need to check that they are identical equations. So we can do this by solving for y. The first equation becomes y equals to 1 over 3x plus 1 over 3, and the second equation becomes y equals to 1 over 3 times x plus 1 over 3 again, if you follow the given steps here. And the two equations for y are identical, so the graphs must be identical also. There are an infinite number of solutions to the system, which means that all the points on these lines satisfy the system as a valid solution. Let's look at types of systems. There are three possible outcomes when graphing two linear equations in a plane. If there is one point of intersection between the lines of these equations, that means that there is only one solution. And if the lines of the system are parallel, this means that there is no solution. And if the lines are coincident, this means that there are infinite number of solutions. If there is at least one solution, then the system is considered to be consistent. And if the system defines distinct lines, the equations are independent. If we draw the graphs of the equations within a system, we can observe their slopes, and then we can easily determine if these lines intersect at some point or are parallel or are actually the same line. So this is why graphing is important for us. Another question is coming. How many solutions does the following system have? We again have two functions, two equations, and two variables. 3x plus y equals to 1 and 3x plus 2y equals to 6. We will write each equation in the slope-intercept form. First equation becomes 3 times x plus y equals to 1. Then we can leave y alone on the left hand side and move 3x to the other side. Then it becomes y equals to minus 3x plus 1. For the second equation, we will get 2y equals to minus 3x plus 6, and if we divide divide both sides by 2, we will get y equals to minus 3 over 2 times x plus 3. And the lines are intersecting lines since they have different slopes. So the equations for the y is different, and their slopes are also different. So if we have two lines with different slopes, they should intersect at one point. So there is only one solution for this system. Another question, how many solutions does the following system have? 3x plus y equals to 0 and 2y equals to minus 6x. The first equation becomes y equals to minus 3x, and the second one becomes again y equals to minus 3x. Then these two lines are identical, so there are infinitely many solutions. We have another one here. The first equation becomes y equals to 2x, and the second one becomes y equals to minus 2x plus 1. Here, even though the y values are different, their slope is the same. So this means that these two lines are parallel lines because they have same slope but different y-intercepts. This means that there are no solutions for this system. Let's move towards another technique of solving linear equation systems, which is substitution. Within this method, we solve one equation for one of the variables, then substitute the new form of the equation into the other equation for the solved variable. Quickly start with an example. Say solve the following system using the substitution method. And we have two equations, 3x minus y equals to 6 and minus 4x plus 2y equals to minus 8. Solving the first equation for y, if we subtract 3x from both sides, we get minus y equals to minus 3x plus 6. And if we divide both sides or multiply both sides by minus 1, we get y equals to 3x minus 6. And if we substitute this value for y in the second question, because we already have a y in the second one and we know what is y from the first one, we will get minus 4x plus 2 times 3x minus 6 equals to minus 8. So we replaced y with the result from the first equation. Then we use the distributive property and the equation becomes minus 4x plus 6x minus 12 equals to minus 8. If we simplify, we will get 2x equals to 4 and x equals to 2. Now we substitute x equals to 2 into the first equation that is solved for y. In this case, the first equation becomes 3 times 2. Actually, the definition of y from the first equation becomes 3 times 2 minus 6, which is 6 minus 6, which is 0. So our computations have produced the point 2, 0. Then we will check the point in the original equations. For the first equation, if we put 2 instead of x and 0 instead of y, we will get 3 times 2 minus 0, which is 6. And for the second one, we get minus 4 times 2 plus 2 times 0, which is minus 8. So the solution of the system is the point 2, 0. That's true. To solve a system of linear equations by the substitution method, we first solve one of the equations for a variable, then we substitute the expression from step 1 into the other equation, then we solve the new equation and substitute the value found in step 3 into either equation containing both variables, and lastly we check the proposed solution in the original equations to see if the found point is a solution or not. For this example, the equations are y equals to 2x minus 5 and 8x minus 4y equals to 20. And here we have to solve the system using the substitution method. And since the first equation is already solved for y, so we are lucky, we substitute this value into the second equation. And we will write 2x minus 5 instead of y in the second equation. And we will get 8x minus 4 times 2x minus 5 equals to 20. If we make the distribution, 8x minus 8x plus 20 will be 20, and we will get 20 equals to 20, which sounds quite different. When we get a result like the one on the previous slide, that is obviously true for any value of the replacements for the variables, this indicates that the two equations actually represent the same line. So it is just like the coincident lines that we have visited in the first method. There are an infinite number of solutions for this system, and any solution of one equation would automatically be a solution of the other equation. This represents a consistent system as we have defined earlier, and the linear equations are also dependent equations. The next one is here. The equations are 3x minus y equals to 4 and 6x minus 2y equals to 4. We will solve the first equation for y. Minus y equals to minus 3x plus 4. And if you multiply both sides by minus 1, y equals to 3x minus 4. So let's look at the second equation. 6x minus 2 times, instead of y, we write here what we have found in the first equation, which is 3x minus 4. And the equation becomes 6x minus 2 times 3x minus 4 equals to 4. And from here, 6x minus 6x plus 8 equals to 4. And 8 equals to 4. So, not so good. When we get a result like this one, that is never true for any value of the replacements for the variables, this indicates that these two equations actually are parallel and they will never ever intersect. And because of this, there is no solution to this system. And this represents an inconsistent system even though the linear equations are independent. And let's move towards the next technique of evaluating linear equation systems. It is the elimination technique. It is also called the addition technique or the arithmetic technique. Here we multiply both equations by numbers that will allow us to combine the two equations and eliminate one of the variables. And after this point, we will get two functions, two equations actually, but containing only one variable. So what we will do here is solving the equation for one variable and then getting the second variable using the first variable. It will best be understood by an example again. So the question asks us to solve the following system of equations using the elimination method, and the given equations are 6x minus 3y equals to minus 3 and 4x plus 5y equals to minus 9. Here we will multiply both sides of the first equation by 5, and for the second equation we will multiply both sides by 3. And why we choose 5 and 3 for multiplication? It is because of the reason why we are multiplicating these equations by a factor. So what we want to do is we want to add these two functions hand by hand. So left hand part of the equations will be added and the right hand side of the equations will be added together, and we will eventually get another function, which is the addition of these two equations. But when making this summation, we want to naturalize one of these variables. So this is why we are multiplying these equations. We want to get rid of one variable, and we want to have an eventual equation that contains only one of these variables. It could either be x or y, doesn't matter, but we want to neutralize one of them, and we want to be left alone with only one of these equations. And this is the elimination method. The first equation, if we multiply by 5, becomes 5 times 6x minus 3y equals to 5 times minus 3. And we will get 30x minus 15y equals to minus 15 if we make the distribution. And the second equation becomes 3 times 4x plus 5y equals to 3 times minus 9. And in the next step, we get 12x plus 15y equals to minus 27. So we can now combine the two resulting equations by making an addition, and thus we will be eliminating the variable y, because when we are adding these two equations together, the y variable will be neutralized and will disappear from the resulting equation. And 30x plus 12x would be 42x, minus 15y plus 15y would be 0. And the result part would be minus 15 plus minus 27, which is minus 42. And from here, x will be solved as minus 1. Since we now already know x equals to minus 1, we can use this as a substitution. And we can substitute the value for x into one of the original equations. It doesn't matter which one we choose. 6x minus 3y equals to minus 3. Now if we take this equation and put minus 1 instead of x, we will get minus 6 minus 3y equals to minus 3. And here, by solving this equation, we will get y equals to minus 1. So our computations have produced the point minus 1 comma minus 1. So what we should do in the final step is checking the point in the original equations. If we write minus 1 for both x and y, in the first equation we will get 6 times minus 1 minus 3 times minus 1 equals to minus 3. And for the second equation we will get 4 times minus 1 plus 5 times minus 1, which is equal to really minus 9. So this point we have found in the previous step is actually a solution of the system. In order to execute the elimination method correctly, we first rewrite each equation in its standard form, eliminating fraction coefficients. If necessary, we multiply one or both equations by a number so that the coefficients of a chosen variable, either x or y, are opposites. And then we add the equations together and we find the value of one variable by solving equation from step 3. Next, we find the value of the second variable by substituting the value found in step 4 into either original equation. And lastly, to be sure, we check the proposed solution in the original equations, and we will see if this found point is really a solution or not. Another example is here. It says, solve the following system of equations using the elimination method, and the equations are 2 over 3x plus 1 over 4y equals to minus 3 over 2, and 1 over 2x minus 1 over 4y equals to minus 2. We should follow this recipe, and we will first multiply both sides of the equations by a number that will clear the fractions out of the equations. So as coefficients, we don't like fractions. We want to get integers if possible. We multiply both sides of each equation by 12. Of course, we don't have to multiply each equation by the same number, but in this very specific case, it will be convenient to do so. If we multiply the first equation, it becomes 12 times 2 over 3x plus 1 over 4y equals to 12 times minus 3 over 2. And the equation becomes 8x plus 3y equals to minus 18. So in this form, we don't have fractions as coefficients. By the way, the second equation becomes 12 times 1 over 2x minus 1 over 4y equals to 12 times minus 2, which is 6x minus 3y equals to minus 24. So we just got rid of the fractions. Now we will combine these two equations by adding them together. And 8x plus 6x is 14x. 3y minus 3y is 0, so y variable disappears here. And minus 18 plus minus 24 becomes minus 42, and x is resolved as minus 3. Next, we substitute the value for x, which is minus 3, into one of the original equations. And if we put it into the first one, we get minus 24 plus 3y equals to minus 18, and y here is resolved as 2. So our computations have produced the point minus 3, 2. Now, finally, we will check the point in the original equations. Here, we should use the original equations before any modifications and before the multiplications to detect any computational errors that we could have made. And if we use this point minus 3, 2, in the first equation we get 3 over 2 times minus 3 plus 1 over 4 minus 2 equals to minus 3 over 2, which is minus 2 plus 1 over 2 equals to minus 3 over 2. For the second equation, we get 1 over 2 times minus 3 minus 1 over 4 times 2 equals to minus 2. And in the last step, we get minus 3 over 2 minus 1 over 2 equals to minus 2. So we already proved that this point satisfies both the equations, and it is a valid solution for the given system. There are also some special cases for the elimination method, and in a similar fashion to what we have found for the previous methods, use of the elimination method to combine two equations might lead us to results like 5 equals to 5, which is always true, thus indicating that there are infinitely many solutions since the two equations represent the same line. Or we may get results like 0 equals to 6 or whatever, which is never true, thus indicating that there are no solutions, since the two equations represent parallel lines. For today's video presentation, that's all. We may or may not be able to continue, but if we will have the opportunity to continue our short course series, you will definitely get to know about that. Take care. Thank you for listening.